Hello everyone, welcome. How are we all doing? So I quickly just want to commit this work that we were doing, and then we'll get started. Git commit. So essentially this was like, start work on top level acceleration structure, but sort of like pause it for now while we work on the LOD and clustering stuff. There we go. Okay, that'll be good enough. So last stream, where's the yeah, what do I want to show? I want to show the tile binning version. This one. They want to disable this one, the BVH render. Okay. So last stream. Oh no. Okay, that's fine. These are meant to be moving. Oh, we disabled the Z. Z equals. Sorry, the rotation. That's what I meant. So last stream we made it possible to have instances of a model. So this dumbbell model that gets generated basically up here, and then we create two instances and we're able to render both of those now. We can actually make more in all of this. There's some glitches, but don't mind those. All made out of spheres, and we're currently just displaying their view, so their local space normal as their color. But yeah, so we can sort of fly around them and they can rotate independently, and that's about it. So I had we wrote a whole list last stream, and we'll get that list up now. Models plan, this is it. So we wrote up a bit of a, oh shoot. Really? When did that get buggered up? Luckily I can keep the undo buffer. Okay, it's here, good. Oh my days. Alright, let's just redo all that. When did it get buggered? I guess that's what I wrote all that stuff. Oh, okay, just there. Excellent. Right. Let's rewrite that. So last time we wrote this to-do list out, and the sort of aim for this sort of set of work is to build a stress test scene where we can have a bunch of models, so we can basically test performance and some we can actually make some features using this, right? And so it'd be a good approximation of, if you have like a scene in a game, what sort of performance could we get? So we kind of did this one. So I was thinking I could tackle these one at a time, and then sort of just tackle the problems as they come. But I think what's ended up happening is, towards the end of the last stream, we tried to do the BVH renderer. So we've got 3 different renderers, right? They're all basically just ray tracing spheres, but they've got different acceleration structures. The first one is a screen space tiles. The second one is a view space Froxall binning. The third one is a BVH, which is in world space. We found out that doing it incrementally is probably going to accumulate a lot of temporary code that we're going to have to sort of write, and probably have to spend a lot of time thinking how is this thing going to end up looking when I've done all of this, right? So I was thinking if I could just do it incrementally, it would probably be better, but I don't think it is. So I think we're going to switch gears. So we've done this one last stream, that's fine. But what I want to do is I want to go over this plan that I've basically written up, and I want to try and plan it as much as possible, and that way we can basically just do like a count for all of these in one go and just build up towards it by following the plan. I think that's what we want to achieve now. So there's less sort of stopping and thinking as we're building. Instead, we should just be able to build the whole thing when we have a full plan. That's the idea. So I think let's just start off. So I did post when I said I've been thinking. This is where the sort of thought process initially came from. It's probably best to delay the completion of the BVH support for multiple instances until the variable ball size and LOD and clustering has been added. I've sort of taken this a bit further now. It's probably best to plan the whole thing. So there's a couple of problems I've got in examples. With the variable ball size, it makes it impossible to use a binary heap. So currently, let's get out the drawing board. I need to configure that wine. Go on, install that mono. So effectively, a binary heap is like an implicit binary tree. You can just use maths to sort of know where the next node is. So as an example, here it is. You've given a node index, you can get the parent index. Given a node index, you can get the left child. Given a node index, you can get the right child, and its sibling, and also its depth in the tree. So it has to be a tree that is even, right? It has been evenly like this can be these can both be binary heaps because they're even, and when you add another node, they'll just go here and they have to follow this order. You can't magically have them getting bigger down one particular path, right? They have to it has to happen evenly. So yeah, when we use the variable ball size, we won't be able to have a balanced tree. So there's that thing as well. This is going to come up. I have to convert all that code over. The model clusters. Yeah. It's the best way to explain this. Yeah, so essentially we want to have these things called clusters. Those are essentially just going to be like a 2 by 2 set of spheres, right? So imagine that just going off into Z one more time. And the reason why it's useful to cluster things together in 2 by 2s is because you can basically make this into an LOD system, because you have a lower level of detail, which is just another cluster of 2 by 2 by 2, right? And another cluster of 2 by 2 by 2, and another cluster of 2 by 2 by 2, and then going, times that by 2 off into the Z, right? So you have 8. And eventually these can be, imagine these are 2 by 2 by 2s. So they have a third dimension to them, and then imagine these are there's also a group of 2 by 2 by 2 groups of 2 by 2, right? Then you essentially have like another level of detail, which is just a sphere that covers all of those spheres. And and then you'd basically repeat that all the way up the tree until you reach, until you reach the lowest level of detail, which would just be possibly one big sphere. Now you would only get collapse these into a single sphere if this whole box contains if it's completely filled with a 2x2x2 of spheres, right? Because otherwise it doesn't make any sense to do that. So these clusters, things will have to be built into that yeah, these clusters also have to be built into that BVH system as well, and I think it's a lot of work implementing it in 3 different renderers every time. And instead we'll probably just be better implementing it in 1 renderer and just get the whole thing working and then just switch everything over to it. Probably just be better that way. So let's go over the plan at least, and then we're going to finish this plan off today, and hopefully we can get started on it. I think we're going to get started on it because we're going to be designing how this stuff works anyway, and this will just be copy and paste some of it. But yeah, so currently if we look at the system, we just have like, how we make these is we just have like a 3D volume, and it's in signed norm space, right? So -1 to 1, and we just pick like a step size of how, we pick how many spheres we want in there. So we've got 20 by 20 by 20, and we've just gone over all of those cells, and we've got a sign distance field function, and we just check if we're inside that sign distance field function. So it's currently just a couple of spheres on each end and a rectangle in the middle. So that's how we build that one. It's just all in code, and obviously we don't really want to build our models this way because it would just be a lot of work to do that. So essentially it's just something like this, right? We just step over in 3D with a step size of 2 divided by 20, and just check each time if we're inside the sign distance field of these 2 spheres in a box, and if we are, we put a sphere down. So it would kind of be good to move away from this system and closer to what we will be having in the long term, really, to make it easier to build more models and stuff. But that's our current system. So what we kind of need to move to, wait, I haven't finished describing it. So currently, if ideally we want these balls on these models to be able to go like quite small, but also quite large. We want to have a bit of freedom when we make these things. So that's where the variable size of the balls comes in, because it would be nice. You might want to have some very small detail, but some maybe you don't really care sometimes. Just want it to be large. So I was hoping, and I think it's possible with this new plan that we've got written out, that maybe we can have the balls go as small as maybe 2 millimeters, maybe something like that, all the way up to some large size. But there is going to be some sort of hacks that we do inside the engine to make sure that's possible, and some restrictions as well. So another problem we've got to solve is when we zoom out, eventually these balls are going to be like less than a pixel, and it's not going to be good if we just render those and have a whole screen filled with it. So you want to have like a different LOD. So ideally it should render a bigger, it should get rid of a 2x2x2 block, a cluster of spheres, and replace it with just a single bigger sphere. So yeah, we need to build. That's the other system that we want to build as well, because otherwise this won't scale very well. So let's get this drink open. It's a bit warm in here. So it's got LOD clusters, which are 2x2x2 set spheres. Wait, each of them can have an empty slot. That's possible. But if it has an empty slot, then the higher level of detail will not be able to. The lower level of detail will not have a sphere. We'll get into that in just a bit. So there's a bounded volume hierarchy. This is a binary tree of nodes, which we've already been over in the past streams. Each leaf node is a cluster. We already kind of have this, but this is just a commonality which we're going to see is this thing called a cluster. And so the bounded volume hierarchy is just one of the renderers that we use. So one of the acceleration structures for one of the renderers that we have, which is ray tracer. We want to use this specifically for lighting because we found out that it's probably not going to be the best renderer to use. And this is what we're trying to prove out by having 3 renderers running at the same time. So this is probably going to be a fixed level of detail given a set of graphics settings, right? As it is only used for lighting. Well, that's the hope, right? Well, that's the plan at least. So some other little things, we're probably going to have like a fixed number of materials per. So I found out a new name for a model. It's going to be called a volume. So that's what volume means, is a model. So yeah, we've got a material palette. So we'll probably have like we want to have a way for these when we create like an object inside this engine. We want to have a way to sort of customize like the colors. You want to have different variants of a model. So one way that I'm thinking about doing that is we just have different, a bit like just have a palette of materials, and you basically paint with a palette, and you can just swap that out for each instance. So I think that's what we're probably going to do. So a material is basically, it's got a base color. It's just going to be U32, or it's going to come from maybe a procedural texture. Stuff I haven't done before, but it could be an interesting idea. So we just procedurally have a set of textures. Procedurally make a set of textures for different. Maybe you have like a wood, like a procedural wood texture or something like that, where we programmatically create these things. And maybe we can get some detail on the bigger, when we choose to have larger spheres. But when we have small spheres, you might not really care about the procedural textures because they'll be so small anyway. You can just get the detail on the spheres themselves, right? Probably just do a PBR setup, right? On this roughness on there as well. Boom. Probably just go PBR, to be fair. Seems to be okay. So we've got a new name for a model. It's called a volume because it's literally just a volume of spheres. And the idea is you can just so there is restrictions on this volume, but when you it's not a fixed restriction. It's a configurable restriction. It's got like a sliding. Yeah, it's a sliding restriction essentially, so it's fine. So with this volume, we're probably going to be, so you'll probably just chain a bunch of volumes together to make an overall model. but there's no concept of a model anymore. So I think we're going to have an octree where each node is a possible 8 nodes, right? So what an octree is. And so this is going to allow us to save memory and on any empty space and where areas have a lower level of detail. So let's expand on this. Like, what is this octree thing? So having to think about it is, we need to solve that problem of LODs and, and we're going to have clusters. LODs, you can think of when you have like a cluster, like you could, where's the drawing thing? When you have like a cluster, you can think of a cluster as being some like, okay, imagine it as this like 2x2 here in 2D. I did just go over this example, but let's just do it again. When you have a cluster, you can think of it as if it's 2x2, and when you zoom out and these things become the size of a pixel or a few pixels, whatever it is, you just want to replace these with a single sphere, so it's less work for the computer to do or to render, right? And you multiply this across like tons of things. It really pays back. But the problem is if you have your cluster at a 2x2 and then you've just replaced it with a single sphere, there's nothing, you can't lower this single unit of thing, a cluster, anymore. There's no lower level of detail. So how do you possibly make it go any lower level of detail? Well, you basically need a tree of clusters that can then become like a cluster of clusters, basically, and then it's a bunch of just clusters all the way down, right? And then you can basically have your clusters of clusters and make a low level of detail there, and then whenever this one gets smaller than a pixel, you make that into a sphere, right? And so on, and you keep going up until you've basically not got you keep collapsing it down until you can't do it anymore. Or if there's a sphere missing from it, it cannot get a sphere because it simply doesn't completely fill the space. And when you zoom out, you lose that detail, right? So that's the reason why we'll need a tree. And this is why an octree makes sense, because it works with that 2x2x2 set of spheres as a cluster, right? It's kind of implicit, or it's kind of an intrinsic nature of the octree. Hey there, it's Musco. What happens if they're all heteronic? I can't even pronounce this word. Heterog. Yeah. What does that word mean again? Heteroneous or something like that, isn't it? Yes, cluster have different materials. That's a very good point. Definitely listening there. So I was thinking, see, the problem comes from this procedural texture idea, right? If we didn't have this procedural texture idea, it will be a lot easier. We can simply just store a full set, even though we've got this sort of palette. We could probably just store these actual values per sphere and then just interpolate them up. But we've got procedural texture, so they could be. So I think currently the way I'm going to do it now is I'm just going to pick the one that's mostly because the idea is you're going to be like painting these spheres down into this grid. So the most common material is the one we're just going to pick. But I think some way we could do it is maybe have the most common 2 or the most common 3 materials, and we probably interpolate those together, like just interpolation. But I'm not sure if but we'll see how that goes in the long term. because I don't really want to have multiple materials per sphere. But if it can work out, then maybe we do, right? Maybe you can take a couple and interpolate between them, and then that is good enough. Yeah, I think that should solve the problem. Okay, I like this. How about fancy low order approximation of the material functions? What does that mean exactly? Can you rephrase that? I can understand exactly what that means. Sweet lemonade. Oh, I got a tea here as well. Let's probably bring that first. Make a new material that approximates the whole cluster. Oh, that's an interesting idea. Right, so yeah, and that's probably possible given the fact that's a really good idea actually. Yeah, let's note that one down. Let's Moscow 1 came up with a great idea. Interpolate, but discards a few details. Do you mean like interpolate between a bunch of materials and store it in a... Because you got these procedural texture ones. Or maybe average the material into a sort of temporary runtime material. I'm not sure how muddy that would get. Like LOD of the combined material. Right, I see. Yes. So it's not really like an average, like a lower LOD, right, of the combined materials into a sort of temporary runtime material. Yes. So that's just a question of space, isn't it? You know, sort of my first instinct is a question of maybe memory or space. Yeah, sort of memory. Yeah, because it entirely depends, but maybe you can sort of share it. We'll see. It's an interesting idea. Jot that one down. So, yeah, so we're going with this octree thing because it kind of like just intrinsically houses the 2x2x2 cluster. I was hoping I can go for a larger 2x2 cluster, so larger than 8 spheres in a cluster, because I was hoping that we can have a nice number for when we write our shaders. Turns out 8 is not a good number when it comes to launching many threads. But what we might do is just do a for loop instead and have one thread per cluster, and that might be okay. So we'll think about that in a bit as we extend this, as we finalize this list. So obviously, each node's children arranged in a 2x2x2, right? A cluster. Each node is a cluster at a different LOD, level of detail. So a cluster is only valid on a node if all children nodes, I should probably say a nodes cluster. A nodes cluster is only valid if all its children nodes have a valid cluster, right? So, if you have, maybe we can be a bit lenient with this, but say if you have 3/4 of a cluster, right? This is just a 2x2. Yeah, maybe, it's 2x2. Then this cannot have a lower level of detail. This is the lowest level it can have. And the reason is because when you zoom out, you kind of need to, you'll be making up this sort of empty space. But maybe in 3 dimensions, maybe anything above 3/4 is fine, right? If you have 7 out of 8, maybe that's fine to replace it. We'll see how that goes. Maybe 7 out of 8 plus is onwards is okay. A question mark there. Each volume has its own BVH, and this would be a bottom level. So this would be a bottom level BVH. So there is if you decide to make tons of, which we'll get into in a minute, very small high quality volumes, there is going to probably be an issue where you're creating tons of bottom level BVHs that go into the top level. But yeah, we'll see about that. But it can be controlled by the people making the content, so it's not that bad. But yeah, it's going to have a fixed LOD, as I've mentioned up here. Since it's only going to be used for lighting and want to avoid pop-in, imagine shadows with pop-in. Ew, right, horrible. The further the node is from the edge, so this is another way we save memory. The further away it is from the edge, the lower the LOD will be, allowing us to save memory on parts that will simply not be seen. And they see for static meshes, static models, right, of spheres, we probably won't see on the inside at all, so we could probably completely get rid of it. But when it comes to something that's dynamic, we might want to keep some of the stuff on the inside. I'm not sure, but the idea, at least with this one, is imagine this is the left-hand side, and imagine this is going inwards, and we've got a whole ton of content going over here. There's a whole ton of spheres and that carrying on down here. The idea is, because these have a assigned distance or whatever, right, which is inside the volume, it would not be possible to have this low quality further inside, because this is the lowest quality here. If these were to jump and move around and you were able to see through, it doesn't really matter if these are a bit bigger, right? It just doesn't really matter. So that means as we go inside, the spheres will get bigger and bigger, so long as they're not near the edge, right? And this will mean we can have things as small as 2 mil, and it won't be a problem because you're basically only covering the surface in 2 mil. And if you can work that out based on the biggest surface area, which is basically take a 2D, like how many spheres on a 2D plane, and times that by 6, one for each face of a cube, and that should be the most surface area. And I've done those calculations and it seems fine. So this is one of the things that will help out with reducing the amount of sphere data that we're going to be storing in GPU memory at runtime. And it won't be a problem. So, right, so speaking about the volume and how big it is, so the volume is going to be restricted to 1024 by 1024 by 1024 spheres at the sort of highest quality. But you can obviously have larger spheres, they just take up more room. But the scale determines the volume size and the smallest sphere unit. So the absolute smallest unit is probably going to be about 1.6 mil. Now, that might be the grid size. We might have slightly bigger spheres, so it might be around 2 mil. But this will give us, this is basically, you can times this by 10. You can times something by 10 times. Wait, sorry. Yeah, you can divide something by 2 10 times, or times something by 2 10 times and reach this. Which will be, yeah, which will mean there's sort of only 10, what does that mean? I'm not sure where it's going with that one. Ignore me there. Might come back to me. So essentially, right, yeah, if we times this by 1024, we get 1.6 meters of space. So this is going to be the sort of the highest quality level of volume. If you want something of this high quality, you can do basically. But I was thinking, then the sort of largest level of quality, we probably want a max model size of like 160 meters in the extreme side. Maybe we can go smaller, but then your smallest sphere units would be 160 mil, which is still quite good. That's 16 centimeters. So this is how we get around the problem of, wanting that small detail in some cases, but also wanting that large detail. So by restricting ourselves to a sort of a volume of 1024 by 1024 by 1024, it means we can use the Morton 30-bit still that we use to create the BVH. And this is how we basically sort our spheres. And there's no sort of complicated stuff we have to do. Just use Morton 30-bit, and we have our spheres, sort them, and then we can create our BVH very easily. I think there might be we kind of would be mixing different LODs. So there will be maybe a bit of complication there, but it should be pretty easy. Okay. My tea's getting a bit cold. Let's finish this. So nearly there now, and then we can basically finish this plan off. So, the problem with a 3D volume that is 1024 by 1024. Wait a minute. I didn't really describe the problem. Describe the thing I mentioned earlier. Yeah. It's kind of about space as well. So if you take out a calculator, if you did 1024 by 1024, that's a million basically. And then if you did it again, that's 1 billion. So that's basically a billion potential spheres that you can fit in a volume. And you must be thinking, if you can have that per model, that's pretty insane. How could we possibly have 1 gig basically of spheres? And it'd be many gigs, right? Because maybe there's 32 bytes per sphere or something like that. 32 gigs of memory, quite a lot. So, there's that thing that we read earlier, which is basically saying that, when a sphere is, or Yeah. If a node or a sphere is further from the edge, it will just be a larger sphere since you won't see it. That's one of the things that helps. Yeah. Sorry. So, yeah. So essentially, further away from the edge, further away from the edge, the larger the spheres will be. So the quality will only be on the edges, right? A bit like with triangles, the quality is only on the surface of the model. But we'll probably have a way to sort of distort the model in a way so you can move the spheres, and maybe you can sort of get a glimpse of what's behind it. So those spheres will need to be there to stop there being holes, but we maybe get something sort of that moves and looks more alive. So with this thing in here, the space should hopefully be helped dramatically, right? So we did 1024 times 1024. You get a million, and then we're probably going to be having 6 faces of that million at most. So you times it by 6. So there's 6 faces on that cube, right? So you're probably looking at around about 6 million. Now, you've obviously got the inside where the quality gradually gets larger, right? So on the edge it might be 1.6 mil each of these guys, then on this one it'll be 3.2 mil, and then as it gets bigger it'll be double that, 6.4 mil, well whatever it is, 6.4 mil, and then so on. It keeps getting bigger and bigger and bigger. So ideally we should be looking at probably 2 times this number if it was to follow maybe of like how the MIPMAC stuff kind of works. Maybe it will be a little bit more, but maybe we're looking at about 12 megabytes of space instead of, maybe it could be as much as, depending on the volume, maybe it can be as much as I don't know, 32 meg, but that's instead of 32 gig, right? So that's much better. So that should work, and that's only if we completely fill the space. I'm sure if they're much smaller and you get rid of the high level of detail in places where you don't want it, that can just get improved. That could just number can always get improved. Okay. So the volumes can be stored on disk, and we've just gone over how big those models could be. They could be probably megabytes. Yeah, but probably around 10 megabytes, maybe to 200 meg actually, because there's all these material properties. Actually, no, because we might be using pallets, so that might be, it could be around 10 meg, 200 meg, depending on where we go with that whole material thing. Which could work, but this could be a lot better. Effectively, there is another way to sort of compress this down. You could probably apply some form of compression where they're just the same, and just sort of repeat that, do like a run length encoding type of thing. But there is a kind of nice, elegant way to do this, and it does mean you can probably actually support undo and redo at the same time. And this is the way it works in Dreams, basically, with the SDF stuff they have. So it's quite a decent idea. Basically, just store a list of operations you did to make the volume. So ours is probably going to be a lot more simple tool set than Dreams was. So we might have like basically just a brush, like a sphere brush, and maybe a box brush as well. Probably won't get anything more complicated than that. But like we're just going to be painting down spheres basically onto a grid. But so with this one, if like as soon as we load, like you pay the price when you load up the model from disk. you pay the price to like evaluate it into that octree. And that's basically where the cost trade-off is. It's actually done at runtime instead. So you're basically decompressing it in a way. So say if on average each edit is like 32 bytes, maybe you have like an edit operation, maybe it's like add, remove, maybe you can paint material properties down, and you've basically got a bunch of edits that you're putting in. So it's basically like a sphere. You can really pack that down into small. It could probably be a lot smaller than 32 bytes, to be honest. This is just a number I've pulled out of my head for this example. And say if you did like 1,000 operations, that would be 32 KB. So, you're probably looking at in the thousands of operations to achieve your volume. And this means when you boot the volume back up, you can actually undo it and have it reevaluated as well. Every time you undo, it will probably just reevaluate the whole thing. And this will be a lot cheaper than just storing the whole tree. And also storing this whole tree is a bit error prone. Like I can imagine this getting corrupted very easily. Like you can basically corrupt the tree if the code was wrong. Whereas if the code was wrong to create this tree, then it doesn't matter because we would have the way we made it all stored in a file. And then we could just basically just reload the game with a new patch, and then it will essentially make the corrected version of it, which is kind of interesting as well. So you're probably looking at in the thousands of operations. There is probably a way to optimize this down. Say if we want to compress this down even more, we could probably, you could probably run a compressor on it, right? That's one thing. But you could also probably be like, we've got our spheres here that are placed down. Oh, I've deleted them all. So maybe there's a bunch of sort of operations that we did to sort of color, to like place these spheres down, right? There's a couple of, we've sort of taken our brush and we've painted a few sets of spheres down. Or maybe you have a whole sphere which encompasses these spheres, which literally gets rid of them. You could probably get rid of these operations, right? So but then again, you lose the history when you do that. So there's many benefits to this solution, but it does have the cost of at runtime. You need to evaluate it again. So to solve the problem of having a volume that we've handcrafted and we want a different skin on it, we're going to probably be having a palette of materials, as we just mentioned, because we saw above. These can be overridden per instance. We're probably just going to go with the solution to begin with, where we're just going to, if you have a group of 2x2x2, if you have a cluster of spheres, which then go into a lower level of detail, we'll probably just pick the most prominent material from that and just use that for now. But as decided from has been suggested by Russ Musco, we could possibly, at cost of extra memory, probably combine the materials into a lower level of detail version of that material if they're procedural textures, and put into some temporary runtime material. That's an interesting idea. I didn't think about that one actually, so we'll possibly explore that in the near future. Right, so that's basically the volume stuff. It's kind of a lot, but it seems like the way to go. If anyone has any more ideas or questions, please feel free to ask. So with a volume, you can have instances of a volume, right? So you make, this lovely, where is it? This lovely dumbbell model. You want tons of this, right? To have instances of it. Each one of these has a transform, and you can override the materials and give it a different skin. Cool. You think spherical harmonics would be a good way to do LOD on clusters. Ooh. I've heard of that. You know, I was researching into what is it called? Direct diffuse. What was it called? Direct diffuse GI, global elimination. And people were mentioning you could use yeah, that spherical harmonics thing. I'm not quite sure what it is. It's quite maths. It's got some maths in it, but I need to learn the maths. If you have any good links on articles or something to read to sort of learn that stuff, please link those in the chat. That'd be nice. But yeah, it's sort of like you have a series of different directions. I've seen it used as, right. You have a bunch of different directions, and you can sort of encode it in like a lower level of information and sort of get understand how the directions sort of behave. I don't know how to explain it. Yeah, you can sort of compress a bunch of information down into a smaller set of information and sort of still use it to solve a problem, I think. That's the way using it for GI, I think. It seemed interesting. Just didn't understand it. Yes, that's volume instances basically, right? And they'll probably have these things called like bundles or something like that. I think Blender calls them collections, right? We'll probably just have like, essentially we just have a tree of bundles where each leaf node is a volume instance. You can have names, you know, each bundle has a name and a transform. As a name and a transform, we can probably just save these guys out. You know, probably some, you know, something's definitely going to be made with like a bunch of different volumes together and just sort of aligned in some way. We'll probably need a way. See, I haven't thought about animation, but you don't animate. You could probably apply some form of yeah, we need to have a way where we could probably skin this. I'm thinking about adding like basically like a bone system. Maybe you can have a way, because you don't want to just skin a single volume of spheres. You probably want to skin multiple volumes of spheres. And yeah, we need to think about. Yeah, I think we can do that ad hoc, like, or just do it afterwards, right? I don't think we need to have it in this design, but that's something to think about. Cool. So that's basically the what we've got so far. I want to finish this off. So what's left is basically like the most important thing is the data structures, right? With most things. So we'll probably design some data structures, how we're going to allocate these things, because that will be, you know, I want to minimize the amount of times I have to stop and think. Basically, I want to have the idea in my head and written down, so we can basically just know exactly what to do. And then we probably want to design how the shaders are going to work at a high level and how that interacts with the tile and frustum acceleration structures and also maybe the BVH as well. Cool. So data structures, let's just probably get these guys. It's a text file, isn't it? Let's probably just put these directly in the we'll put these in a section. And we'll just get designing. Basically, so the plan is I want to design a data structure for bundles, volumes, clusters, materials, BVH and the edit operations, and just get that all sort of designed, basically. Hey, the buffet, how's it going? I can see that you program. Yeah, definitely, my friend. Hey, there's something really cool as well about this project. We also have a little C compiler, a little custom C compiler, which allows us to write shader code in C. See here, it's a compute shader, all written in C, has some restrictions, but we've even got printf as well. Got buffers, texture support, pixel shader, vertex shader, but I don't use those in this project. But yeah, all runs on the GPU, compiles for SPIR-V, runs in Vulkan. I write in the fastest language with no overhead, Python. Sounds legit. Yeah, must be extremely fast. This is since the whole thing's written in C. Yeah. Nah. Yeah, Python's notorious known for being quite bad, really. Also, it's kind of a shame on the syntax as well. It's just so damn ugly. Oh. Can't tell where things start and end, you know? Yeah. So let's start with the bundles at least. So these things on disk, they're gonna have like an on-disk version. Like they're gonna have a CPU side version, and a GPU side version. So they need a transform, right? And essentially it's like parent from bundle. So it's going to be a tree of these guys, right? So yeah, that's something to think about as well. If you have a tree of these guys, like you can, you'll probably want to have a way where you can get it into world space very easily in the yeah. So this would probably be like see, I like to prefix stuff with data when it's going to be saved out to disk, basically, or serialized around. So I think you basically just have a version. This is going to be CPU side. So you'll probably have like a so leaf nodes will have so if it's a leaf node, it'll be an instance. This was the union. I'm not sure how I'm going to read. We'll probably save it just as a text file anyway, maybe. So probably doesn't have to. Could dump it to an in-memory version as well, maybe. Maybe. So you possibly have 8. So yeah, either it's 8 of these. So either it's not a child, or it's a what's known as a volume instance. Volume instance. So you'll probably have one of these data structures as well. Yeah, you need a name. So you probably have a... Yeah, I prefer using IDs because we can serialize them out, you know, quite easily. So you have this sort of volume instance that'll probably just have a data volume ID. And then you want those material things, right? Things that can be serialized out. Got my compiler to do hello world yesterday. Oh yeah. So you guess you link to that C standard library and call the printf? Or are you doing a system call? Do you do the system call instead? So you probably need a material. So this is all serializable stuff. So for now, I think we'll just do sort of a base. Right, let's get the type defs for, what is it called? Core define ID. I think that's the thing. Oh yeah. Just defines a wrapped integer, basically 32-bit integer. So you want sort of like a volume ID. You want probably a bundle ID. What else do you want? You need a procedural. So a procedural texture is probably just going to be built into the game. I don't know if we'll allow any more to be made. So you'll probably just have a procedural texture. You probably just have a procedural texture. Maybe let's just do the most basic one that you probably do first, and that'll just be like wood, right? So you'll probably have an option for a procedural texture or a value for each of these guys. So that could probably be just encoded as U32s all the way down. So you could probably just go, oh, this is the base color. So this would just be like, you know, sRGB or procedural texture. Then you'll probably have, you know, just do the whole PBR setup. Roughness, probably keep it U32. Just reinterpret cast that. No biggie. And then metalness as well. So, sorry, not sRGB. Damn it. F32 or procedural texture, that's what I meant. Okay, so this is just what's going to be serialized out. To disk or something. See what the runtime format will be like in a bit. A link to libc, but for now I only used to write from uni standard. Not sure what you mean there. Yeah, so on a material palette, this thing will be saved out. as well. So you can have a palette of materials. So you'll probably have material ID as well. Oh, has the syscall? Yeah, are you using are you right now? Wait a minute. Are you compiling to C or are you using assembly? Like, or encoding directly out to the opcodes, you know, the instruction set architecture yourself. Like, what are you doing? Because you shouldn't have to link to libc to do any of that. Yeah, but it's simple, right? Yeah. I understand you're calling the right function in libc, but the question is, do you write out assembly code, or do you write out the executable manually? I use crane lift. Right. Because you know in you know syscore, I forgot what the opcode number is, but it's just an opcode, and you can, you know, I think the right is like 1 or something like that. You can, I forget these things, or it's 2. I don't know. You can maybe I'm incredibly wrong on that, but yeah, you can just basically have an opcode, sorry, a syscall instruction, and you sort of set RAX to something, and you know, to like a char pointer or whatever, and call that, and off you go, right? That's so if you're doing the assembly, it's just way easier just to do that. Ah, a stringlet. Yeah, quite easy to do a string length, right? Dereference pointer. Yeah, increment pointer. But yeah, you can also do that. You can also get printf as well. It's another benefit. Fair play. Hey Taxa, how's it going? Welcome. Hey Zaka, welcome. Material IDs. Probably have 16 of those boys. Off you go. Obviously you want a nice little name. Now these names, right? We probably just want like a fixed, we'll call it like a data name size. So this would just be like, oh, maybe you need to support up to 32 like characters or whatever for any assets that we make. Ought to be good enough. Serialize out nice and easy. Easy peasies. Names everywhere, eh? So okay, this is looking quite good. Material. Wait, what's that volume ID in there? Right. Get me out of there. Material palette, just a bunch of materials. Probably need a palette ID as well. So your instance is a volume and a material palette. So then we've got this sort of bundle, which is a tree of bundles. It's got a name, parent from bundle. We'll probably make it so each volume instance, when it's on the GPU, has a world from local, right? We evaluate this bundle tree and get that sorted out, right? But yeah, this is just the serialization data. Maybe there's a runtime format, then a GPU format. That's typically how things tend to go. But this is just a good thing to keep on, to have a grounding on what's going on. Cool. So let's keep going with the data structure design. So this is how it looks. Oh, we're missing one more thing from the serialization format. We probably want to have the edit operations as well, because that's the other thing that gets serialized out, isn't it? So you got the BVH that's not serialized out, then the edit operations as well. Now these boys. Oh no, I work in the games industry. I do graphics stuff, yeah. Yeah, I'm off for Christmas break now, which is quite good. But I stream Tuesdays, Thursdays, and Sundays. Do I do competitive programming? Not really. I don't see. I think competitive programming is like probably interesting when you're starting out, or interesting when you are looking for a job and trying to, hone your skills in for those tests that they do. But doing a project is difficult enough, and sort of, I don't know. I feel like it's just better just to train myself doing the actual project, right? They take enough work to accomplish and complete that it's probably just worth not taking the eye off the ball and just getting the project done, Yeah, I don't know if jobs is a good idea. What does a DSA mean? Sorry. But yeah, it's kind of really crazy how much you have to go through to get a job now. It is very competitive. Hopefully, I don't need to do that for a long time, and when I do, hopefully I'm hoping that I don't have to actually do it. Right. Hopefully my resume speaks for itself and I can just get a job at some place, right, when that time comes. All my days. Because some of them are like this heavy C++ OOP thing, and you're like, I sure hope my job isn't like this, that they ask you to do. I think APOC is asking their tax that question. Yeah. Bum, 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 bum. So we need to have those sort of like edit things basically. Oh my days. How do we know if we're a leaf node? That is the question. We probably need a bit. We need a boolean to say is leaf. Right. Sort that out when we actually need to do it. But that'll do for now. So we also want some other bit of serializable data. This is going to be our sort of our volume edit. So we haven't really got a volume. Probably also have an enum of volume edit operation. So I reckon we could probably just do U8 for that. So you probably just have like a data volume edit op. So we've got to think about these, but I think we're going to have like essentially add, remove. Yeah, so add, remove, and you probably want to like, you know, you're probably going to be painting on like some form of property. So maybe paint, color, paint, roughness, paint, metalness. So something like this, right? So each one of these sort of volume edits is going to have like an op, and you'll probably just union it with like some form of structure. So I think the sort of you probably want like a shape. We're probably only going to support a couple of shapes because I don't think we'll need many complex, like, not circle, sphere. What's a 3D rectangle? Is it in a cuboid? Hyper rectangle, no. It is a cuboid, isn't it? So what's a cube called? 3D cube. Oh, it's just called a cube, isn't it? Right, obviously. Yeah, cube and then cuboid. Gotcha. Gotcha. No. I'm looking. I'm not looking for a job in any way. I was just responding to Taxa. I was saying like, I remember doing it, and they were like painful. Did I spell cuboid right? Good. Cuboid, as they say. But yeah, I'm happily in a job right now, and I don't see myself leaving for a while. But when that, when the time comes to get another job in the future, I'm hoping I don't need to do that whole interview process where you got to go and do some basic BS test. You know, and compete against a bunch of people. Well, yeah, I'm hoping you have to do a basic test when you can just show your resume and your work, and then just have an actual interview rather than doing all these silly tests. No, I never do leak code. I did answer that question. I don't like to do these things. I just like to do projects that, working on projects is hard enough, right? So it's easier once you have worked multiple roles and you don't have to do all those stupid technical tests. Fair play. That's good to know. Excellent. That'll be good when the time comes. Ellipsoids. Always ellipsoids. That's a good point. Rosco wants to get me with ellipsoids. Yeah, it makes sense, right? It's good with the naming, isn't it? We can do ellipsoid. That makes sense. Think about it. If we're doing cuboid, it's not just for naming, right? Like, first of all, they both end in oid. But the main point is you have you'll be able to extend the 3 dimensions of that cuboid when you're for your brush. Why can't you do that for the sphere that you're painting with, right? Good point. So what sort of would you just have? So that means then you'd literally just have a float 3 center position, and then an extent, right? So this is a, what's to be a half extent, half dims, right? And then, you know, voila, that just makes a ton of sense. So you need your shape in there. Then it's either just a cuboid or ellipse, and boom. So then all your operations are literally just recorded in there. This could be quantized, right? Because it's 1024 by 1024 by 1024. So what does that mean? Well, we could probably compress 6 floats down into something like fixed point or whatever. We have a base rotation. That's a good point. Yeah, you just don't want to be like, yeah, definitely a rotation. And a scale. No scale. So you probably store the rotation as a probably quaternium. Quaternium is probably best, isn't it? Yeah. What to call it? Yeah, quat. We need to make a quaternium. Very good point. So quaternions can be compressed pretty easily. You can just quantize it again. And then you can drop the W component as well. But yeah, we'll do like a to-do quantize. Is that how you spell it? Yeah. Oh, okay. So you're just saying just use Euler angles, right? I'm not sure how you pronounce that. I've heard people say Euler, but yeah. Do you think the Euler angles, right? So we probably like quantize these boys down into like. So just regarding these positions and things, right? You're in local space of the volume, 1024 by 1024 by 1024. You're probably gonna have like, you know, I imagine having. Oh, that's not what you meant. Right. Okay, what you meant is just dropping the. Yeah, you can just. They all it's normalized, isn't it? All adds up to 1, so you can just, yeah, definitely. So 1024, you probably want to, probably get away with a resolution of maybe 32, maybe 32 per block, maybe, where you record where it goes. Maybe we have a higher resolution, but that might be our sort of our max. Yeah, we can fit it to 16 bits. So you did 64. So given a sphere where you have your position and your half, yeah, for your position, maybe you have a sub step between it each. So whatever, 30. Yeah, 64 or something like that. Because given the sort of largest size is going to be, 16 centimeters, I think that will be fine. Yeah, so you can quantize these down to basically U16 times 3. And you probably just want to say like the scale, um, the data volume, edit, center position scale. So that is just essentially 64 times, or it's 1 divided by 64, isn't it? So that'll get you down to that'll get you down to 1K. Maybe. I think we're going to have some off by 1 errors. 1024 is not the max value. Technically, it's 1023. But yes, there's your max value. Um, hmm. Yeah, how would we sort that out? Or we could just store it in fixed. We could just do a number of bits and just do a fixed point thing where we shift them around and convert them into a float. We can just use how many bits? 64 bits of step. I think it's 6, isn't it? Because yeah, there you go. So you probably use the first 6 bits for the substep and the remaining bits in the 16-bit integer for the remaining 10 bits for the integer part. Perfect, there you go. Okay, so we'll probably just say center position fixed point shift probably be 6. So what about for the half dimensions? So this one, you probably just use the same thing. You could probably get a bit more of a resolution, but it doesn't matter. It literally doesn't matter. Maybe it'll work for the whole thing. See, for the rotation as well, how are you going to quantize it? Should we do like fixed point, or should we do? It's subnormal though, isn't it? Sorry, it's subnormal. It's yes, it's in a 0 to 1 range, so it's probably better if we just have some form of multiplier. You've got could you do as low as 8 bits per? Like for a rotation, could you do it as low as 8 bits? Like so your step for that would be 1 divided by 256, which oh, it did work in there. It'd be that low, right? Surely that's enough. I think there's other ways to encode rotations. I think there's different ways you can encode them. But this isn't a bad way. We can use 3 bytes. But then we're kind of a little bit... yeah, I think there's a way to encode... No. Yeah, we'll probably just use 3 bytes. So I think we can just do something like U8 times 3, rotation. This is a quaternion. The rotation symmetry seems you can limit the orientations. Or rotational symmetry means you can limit the orientations you need to express. Ah. That's another way, right? Right, so you can only... Each 90-degree step brings the cube back to itself. Right. Same with the ellipsoid as well. Yeah, that's true. You could do that. And then that means you can basically you have to modify these things as well. But I think the downside of that... No, there's a downside of it as well, but that's an interesting way of saying it. Right. We could do that even more. I'm going to write this down as a to-do because it seems like you can quantize it even further. That's an interesting take. Rasmusko, you had another label with your name in it. Let's do it. That's a good idea. Sort of, ellipsoids and cuboids have rotational symmetry. Each 90-degree angle sort of brings the cube back to itself with the components, with the sort of half dims swizzled, right? Okay, lose the one. I'll do it. Rasmusko is a great idea. So this one, yeah, so we can exploit this. We can exploit this to possibly quantize even further the rotation even further, or maybe get more resolution and still keep the same size that we're hoping to get, something like that. But that'd be amazing. That'd be really cool. So obviously this is just a quaternion with an implicit W. So we've got to make the W up because just all adds up to 1, so it's pretty simple to make. So this one is going to be the rotation. So you pick up a value and then you multiply it by 1 divided by 255, maybe? Might be 255. Yeah, that's what I was missing out on. That's what I was doing it wrong with the other one. Right. Yeah. So rotation scale. And voila. So this would mean that's a byte, that's another byte. You could probably pack that again, right? You can pack that into a single byte. And then you got 3 bytes. So yeah, you know, to do pack these even further. Right. So just alone, each one of these is going to be 2 bytes. This is 5 bytes. Then you've got, damn it, maths, 12 bytes there. Right, so 5, wait. Yeah, it's basically 6 bytes plus 12 bytes, 18 bytes of information. I did say in the example we'll probably only need at most 32 bytes, but we're in 18 bytes. With this stuff here, we could probably get it down to 16 bytes, and that would be amazing. 16 bytes for every one of these. That'd be awesome. So to do, perform the below to-dos and aim for 16 bytes. That would be amazing. Cool. So that's basically the data that we're going to store on disk. Yeah, this is the data we're basically going to store on disk. There will possibly, there'll possibly be some changes, but this is basically it. So can I get like a section header somewhere? Is there a section header that I took? Yeah, here's my boys. So we'll plop these in here. This is the sort of serialized data, right? Now we want to have some more of a, let's plan out some more data structures as it's the most important part of programming. So now we've done it when we save it, we kind of need to have it in a GPU format, right? So we bring these guys we've just written off disk. What is their GPU format, right? Yeah. So this one is going to be the sort of GPU. This header will go, but I'm just separating it for now. So we've got to basically make a GPU version of all of these. We'll basically strip stuff out. We'll probably use raw indices instead of these ID things. There'll be some other changes as well. Like these edit things will just be turned into an octree, right? So I'll build that octree instead. So we need clusters, we need spheres, and then we also need to probably have a sphere that's stored inside of this sort of octree, and then a different sphere that's put into the tile binning, right? Sort of thing. Right, I'm just gonna go and get another drink, get some more water, and then we'll crack on with this. Right, BRB. Get those tunes going again. Right, welcome back everybody. Oh, house is in order, things are good, so I'm back. Right. GPU data structures for all of these things. So a procedural material will probably just be a texture, texture, 3D texture. Yeah, that's made with maths. Maths. A material. What suppose this material not got a name? Excellent. So the material on the GPU, I don't know what this will be like, because you want to have it. Yeah, I think we might. Okay, let's bring these boys over. How many of these do we want? We want the palette to be brought over. We also want the so See, I'm just thinking. No, yeah, I was thinking maybe you don't need 16 IDs. Maybe you can just make them like chronological, right? But then again, then I just realized the material palette can have a different material palette can have share the same material IDs. You can't have them chronological. Yeah, let's take all those, bring them over to the GPU side of things. So these are just gonna be the probably just live on GPU. Should we prefix them with GPU? Probably not. Alright. Let's get these boys going. So, GPUs cannot have unions. They cannot have strings. So let's get those in there. So we just get rid of the name, right? Because the name on GPU is pointless and don't really support it either. So this will probably be sRGB or procedural texture. That's fine. This still works the same. We just lose the name. So when you build up the game, you have a bunch of materials that are probably saved in some format. Load them up, upload them to the GPU in the same order, basically. I don't know if you'll be able to, like, you must be able to edit and make these. Yeah, you must be able to edit and make these at runtime and make more, basically. But that's fine. That can all happen still. When you make changes, just upload them to GPU. That's fine. So, material. Material palette. You might have a bunch of material indices. So they're essentially yeah. So a bunch of material indices. So we just don't have an ID with some counter in it. Just have a bunch of indices, that should be fine. We could probably quantize these down to 16 bits if we really wanted to, and half the amount of data there, but I doubt they're going to be a problem. I'll just increase cost of fetching the material ID. Right, so volume instance. See, we didn't do volume. That's one thing we missed out on. Can I quickly do that one? So volume is probably just going to be, you know, like everything, has a name. And then you probably just have an array of these sort of edits, if we will. We don't really had arrays of things yet in this data format. We have, they've been fixed sized. That's fair play. Yeah, that must be good enough. So that's the only thing we were missing, is the volume. So the volume is going to be like a tree on the GPU. Okay. So in terms of like, so your material, your palette, that's fine. Your volume instance, where is, okay, the transform doesn't exist in this instance yet, but it will do now because this is one on the GPU. Whereas the other one it was kind of like just a bunch of these collection of things called bundles, right? Where essentially there's just a tree of bundles, and if it's a leaf node, it's a volume instance. Right. So in terms of a volume, like, so the CPU is like, you know, it evaluates this sort of tree of bundles, and it just goes, yeah, I want to just render these instances. Like, the whole bundling thing doesn't really make its way to the GPU in any way. It will be incredibly pointless for the GPU um, to use this, I reckon. But yeah, you just say to the GPU, all these instances, and it's not. This is a world from local, right? Your volume ID, which is now just a volume index, since we don't need any sort of generation counter on that ID. This is a palette index as well, since we don't have a generation counter to care about. That's CPU side runtime information checking stuff. So ideally we want something like this. Yeah. What else? So we've now got this thing called a volume, right? What is this on the GPU? So technically, well, these volumes do take up quite a bit of memory. You know, GPUs nowadays do have quite a bit of video memory, but we might not want all of them loaded at once, right? You might want to come in and load. What do you want to do? You could probably like stream them in as a level loads, right? Or as you get to, but you need a way. Okay. So you could probably have it sitting on. You could probably just have the metadata loaded. These things take up KB of memory, so you probably wouldn't have them loaded. Yes, yeah, sorry, you probably have them just loaded, right? You have a whole level loaded in memory, but in terms of on the GPU, you may or may not be in a certain area where this thing is needed yet, maybe. So potentially these things might not be loaded yet. And when you sort of say you've got this volume instance to render, you can check if the volume is loaded yet, and if it isn't, we can then get it to be loaded, and then maybe in a frame or two, we'll get it loaded, right? Something like that. But for the most part, it will probably just have a few things, right? We need the sort of, should we call it the LOD tree? The LOD tree, or we could call it the cluster tree. Cluster tree sounds like a good name. So cluster tree nodes start index, or root node index, and that will give us an index into the the cluster tree buffer thing. You then want a BVH. So your BVH is going to be loaded loaded with a fixed LOD. So we should probably put a comment say nah. Okay. BVH tree root node index. So this is for lighting. For lighting is at a fixed max LOD based on graphics settings. This one is what we will use for, we will traverse this in some way. Maybe we need to know the leaf nodes or something like this. I need to think about this some more actually. How do we harness the power of the GPU to select the right clusters to render? Because the really nice thing about this system is, where's my lovely cube drawing from last week? Here it is, look at it, it's lovely. But basically there's only 3 sides of a cube that are visible, right? Is that right? Yes. But technically you're not drawing a cube, right? There could be stuff that comes out from this face out here, or this face could technically have some sort of content yeah, some other part of it that comes out and is exposed. So for the most part there could probably be some method where we like where when we're selecting from this sort of cluster tree, I was thinking we could probably put a plane through it. I would probably stick like a plane through it and do like a check. Do like a check if it's on one side of the plane or the other side of the plane. But I don't know how possible that would be. Or you probably want to find a cluster that doesn't have a free. Yeah, you probably want to somehow find a cluster. Yeah, that's probably what you do. So you loop over all them at the lowest, sorry, the highest level of detail. All the threads going ham. And they might check, do I have a neighboring cluster? And do I have a neighboring cluster that is this side? So, you know, this side of the face, this side of the face, or that side of the face. And if it doesn't have one on any of those visible faces, right? So one of the, sorry, in the directions of one of those visible faces, then it means it could be visible. But it means like stuff here that's kind of obstructed by this would be, is it right? No, I think this is just if it's a cube. I'm thinking about maybe if it's, no, I think that could work. Yeah, I think that could be the algorithm we could use. And that would save us from using stuff that is completely, there might be a better way to do it though. I need to think about that. Yeah, that's completely obstructed by these faces. We will do some other form of occlusion culling as well though. There might be some other way where we can reduce the amount of stuff that needs to be occlusion culled. Since these clusters are very small, it'd probably be a good idea. Yes, this is for, for the main rendering. Variable LOD. Based on camera. Hey Sammy Hacker, how's it going? Not doing bad, not doing bad. Yeah man, it's going good. We're just kind of trying to plan out how we're going to be doing our models, model instances, and level of detail, clusters, all sorts. Just planning it all out before we go ahead and execute it all. So I've been running up this whole plan this morning actually, and I've sort of gone over the whole plan at the beginning of the stream. And it's going over quite good, I reckon. I reckon we can get, because essentially one of the other things we're doing as well is having like a variable size of balls, which means we could probably make the smallest unit, this is the hope, 1.6 millimeters, which would be pretty insane. So we've got model instances working, we've got that working last stream. So it's just, this is a 20 by 20 volume filled with balls, and it's very limiting right now. We're trying to add like level of details, clustering, so we could possibly, the whole idea of adding all of this stuff is to build a complex scene and be able to stress test performance and just see what, how much stuff can we fit in a world that's filled with spheres. How much, just really just see how far this idea could actually go. And then also have a test scene that we can do some features on. So like probably some lighting and other graphical features as well. No, we're not using meshes. Yeah, no triangles. No triangles. Actually, Ross must go. I haven't told you my thoughts on how we might do an occlusion, an improved version of the occlusion culling that didn't quite work out before. And it might involve a software rasterizer for triangles. Because I think I want to write very low quality, very low pixel, but I want the pixels to be, I want to write as least pixels as possible, but I want the occlusion to be as precise as possible. And I think triangles might be the way to do it. So we might have a bit like Nanite, where they have a super optimized tiny triangle rasterizer, and I think I might do that for the occlusion culling, but all on GPU. But yeah, that's spoiler territory for some plan in the future. Yeah, I've been thinking about that as well. I haven't written that one out, but occlusion buffer V2 basically. I want to probably just, as much as I do want to do triangles, it might have to happen. Nice looking good. Last time I was here, this was 2D engine. Awesome. Yeah, it's coming along well. Yeah, just dealing with the complications of 3D, but it's getting there. Trader, I'm sorry, Kid Pain. Please forgive me. But yeah, they won't be visible to anyone though. They'll be behind the scenes triangles. You know what I mean? They'll be only used to increase performance for the other renders. So what else do we want on this volume? So we've got the BVH tree, we've got the Oct tree. Okay. They probably need a Do they need a... You probably want the size of the... So when you have a volume, do you want an access line bounding box? Or do you want a... Yeah, you probably want it encoded in the volume. It's U16 times 3. You probably want a... you probably want the dimensions of that, right? Oh, that makes it nice and rounded. I like that. In the data. Oh, each bundle should probably have its own bounding box. Right, and you have the position from your parent. Yes, you probably want a F32 times 3. You probably want its dimensions or half dimensions at that point, I reckon. But this is stored on disk. Yeah. Yeah, you want that. You want that in bundle space. Good old bundle space. Yeah, that was useful. So for a volume, this is not volume instance though. Yeah, it's gonna be awesome. Like considering we built. Oh, sorry. When did we start this project? I don't know how long it's been going for now. Probably 6 months. Right, I released my compiler, took a break, got things together. It's probably been around 6 months now. And this is a good time. We've built so many things. We've built input system, UI system, GPU subsystem. We're doing graphics now. We're running on Windows and Linux. So, add another 6 months, gonna be in a really good place. Gonna be probably towards the end of the graphics R&D, maybe even finished it. I am taking a whole month off in February, by the way. Is it February? Yeah, whole of February. I'm going to Australia, so we're not going to be missing a whole month. But yeah, I reckon we can have like a full lighting thing, and the R&D done for graphics by then. So it's gonna be cool. Maybe be doing a bit of game design by then. I'm not sure. So in terms of like, do you need like a acceleration? No, sorry, AABB anywhere here? So for this volume, you kind of want those. So like you've allocated room for a volume. Like, so if I were to make an edit to this volume on the GPU, you'll probably load it up into some 1024 at 1024 place that you can just sort of edit. And then make edits to that. It will probably be useful to store the dimensions of that. So this will be sphere dims, grid dims, or something like that. I don't know. But how many? Yeah, something like that. Now, what else on GPU do we need to? So you kind of have that sizing thing. I remember that volume had that sizing, where the absolute smallest unit is 1.6 millimeters. So could that just be a transform? Right, just a scaling thing. Or is it actually built into the... Because... Say if... Because I can imagine you have this blank canvas and you kind of don't know where the bounds are on this. When you're sort of making the structure, you might realize, crap, I've reached the end. You need to drop some quality or something. And yeah, you must have ways to... Yeah, you can drop some quality. Maybe you must have a way to sort of downgrade the quality or something. No, maybe that'd be a bit sketchy if you had that. They'd probably have to redo it again, or their parts again manually. Yeah, I'm trying to think what is any other useful information. Yeah, so I guess this could just be scaled, although... Yeah, it could just be done with transforms. My issue with that, though, is... Yeah, you want to make sure that the spheres are kind of similar sizes, but I guess we'll make it easy for you just to do integer scaling. And that way, say if you have like an arm and you want like really high detail on the hand for some reason, that goes into really small spheres. I don't know. You would shrink. You would have the sort of hand in a higher volume with higher in a volume where the spheres can go smaller, but you have less of an overall model size, and then you can sort of just... No. Sorry, what I was thinking is like, maybe you have a hand which has sort of like a... You sort of just build a larger hand, and then you just shrink it down and stick it next to where the arm is or something like that. Yeah, I think that's what you'll probably end up just doing. That'll work. So we'll just use the matrix transforms for that, so you don't have to store any of that information. Do you want to be able to vary how much the spheres overlap? Interesting. So in terms of overlapping spheres, we definitely want to minimize that as much as possible. So within a volume, there's no overlapping. Within a volume, there's no overlapping. When you have two volumes, when you have two volumes which are sort of in the same sort of if they're in the same bundle, that would mean two volumes in the same bundle. You could, like, the artist who's putting it together, or the person who's making it, right, can technically make them overlap, but we should kind of avoid that where possible. Try to minimize that as much as possible, and in the game, I probably want to minimize that by having proper collision volumes, which kind of separates them as much as possible. So separation is fine. I guess the problem is... Oh, I think you're talking about something different. But let me just finish that explanation. The problem with the overlapping comes from the BVH. When you're tracing a ray, the more overlapping stuff you have between two bottom level acceleration structures, the more you'll be traversing all the way up and traversing down into another. You'll finish your one model, and you'll have to traverse all the way down into another model. And ideally, you want to minimize traversing down more bottom level BVHs than you want to. So that's only for lighting, which is probably the most expensive thing anyway. But you're talking about overlapping spheres enable flatter surfaces. So yeah, this is what we're this is what you're talking about, right? Where so each grid, these are laid out on a grid of 20 by 20. I've actually made the spheres 1.4 times bigger than a grid cell here. I think I'm going to go with this look. I'm not sure though, but I think I want to go with this look because it means that the occlusion will work better, because I can group the 2x2s together and guarantee they're not. There's ways I can guarantee there's no holes, especially at different angles as well if they start to separate a bit with animation. We can guarantee when they're a valid occlusion or occluder, shall we say, right? Yeah, and it does they do kind of look a bit yeah, they do look a bit flatter, I guess. Yeah. The bigger you make them, the kind of flatter they would be, isn't it, ideally? In some sense. Because they overlap. This is fine. I'm not sure. I think it's going to be a fixed thing for the whole game. I don't know if I want to control it per model. That is a question though. Because it might look terrible, or it might be an artistic thing that I might want to have, right? Is can these things be configured? Yeah, I'll probably write that one down, because I'll write down as a question mark. But I don't know because the benefit is having them bigger is it means we can do the occlusion thing, but I'm not sure. Per volume you need a separate parameter. Yeah, because it could be an override per instance, couldn't it? Well, yeah, or it could be per volume rather. Yeah, when you design the volume. Yeah, or it could be an override. Yeah, that's an interesting point. Right, do we even want this? Because it could mess up with the occlusion volumes or the cluster occlusion. Because the problem is you start seeing holes, you see. If we go to the here it is. So this is just back to the way it was. You see, you used to get these gaps. This means that our occluders will have to be each sphere rather than a 2x2x2. Which can still work. Square root 2. Did I have that in my code somewhere? I don't know anymore. That's trippy. If alpha ellipsoids and holes, alpha grass. Yeah. You see, the other way to fix this problem. The other way to fix this problem is I was thinking about offset. Like if I didn't have the big spheres to patch the holes. See, the holes might not be a problem, actually, because I could probably just make each sphere an occluder, which might not be that bad. I just thought grouping them together as 8, 2 by 2 by 2, meant that occluder object could be, have less occluders to calculate and rasterize. Um, it depends how many spheres that we have. What was I going to say? Yeah, so the other way of doing it, and this would kind of mess up, is you could basically offset the spheres every other grid cell. So you could essentially make them. Where's a way to draw it? Oh, is it square root 2? Ah, interesting. Thank you. Right, so that's the perfect cover, is it? Nice. Right, so we're looking at... Wait, what am I trying to say? What was it here I was going to? What was this? Okay, lost my train of thought. Oh yeah, the holes. Got it. So basically we can have a grid and essentially we can lay our spheres, right? Currently we're laying them like this. But imagine if we did this. Every other x coordinate that maybe it doesn't fit in the holes. Yeah, if it's a perfect one of these, you still get a bit of hole. You still get some holes here. Yeah, you would reduce the amount of holes though. Possibly, I'm not sure. It's hard to tell with my incredibly not precise drawings. But yeah, you would slightly get rid of the holes, basically. If you angle the axes with 30 degrees, you can stack the spheres. Like this, or I mean rotated? I'm not sure what you mean. I'm trying to work it out. So if you angle the axes with 30 degrees, you can stack the spheres. Oh, one axis. So let's say the y. Triangles, all three sides, limits 1. Hmm. So I don't know what, so you can stack them. Right, because then this will come out to, you got the Z component. I'm not sure. Yeah, I'm not sure if I can wrap my head around this. I'm not sure what I'm trying to figure out. Yeah, maybe it's an interesting idea. Is there a way that you can maybe draw it or to articulate it to me? Hmm. Yeah, I don't know. Um, but yeah, so yeah, it's still up for a question, really. Do I want to allow for different sphere sizes per volume? Because you could do some different uh, filling models from that, right? Um, there could be some artistic element to it. That is for sure. But then we possibly lose out on the occlusion uh, side of things. So, yeah, maybe. Anything else that we need in this volume? So, if it's unloaded, these be U32 max. Maybe you have the edits start index, edits count. So these be stored in some array somewhere. If you want to yeah, so you have these in some array somewhere. And this could be unloaded. Yes, you got your shaders, and they'll sort of create these cluster tree, this cluster tree and BVH tree. Something like that. Okay, I don't know if there's much else that we need for that volume on GPU. Yeah, so when you edit the volume, you'll copy this into some temporary place. Edit in there. And then probably put it back into here and send it back to the CPU so it can save it out. Have a nice day, Noppy. Thank you for coming. So volume. What else do we want to have? So we've done volume instance, volume. Now I need to build the tree and the BVH tree. So let's just do the BVH tree because I know we've basically got one, but we need to change it, right? It can't be a binary heap anymore because we've got our level of details. And it's just a lot easier to build it. So I have a volume BVH node. And this would probably be like our BVH node. N is number of spheres. Should probably link to a cluster. So cluster index. So we need to write some form of cluster allocator. So our BVH nodes can probably get allocated in some way on the GPU as well. Just think about that. But you have like a cluster index, a link to a cluster, and that have the number of spheres in a cluster in there, I think. So then let's make that cluster structure. Do we really want that? Maybe call it a volume sphere, and you just link to a bunch of spheres. Right. This is what we'll do. We'll type def AU32 as a volume cluster spheres, and this would just be a. You have a way to sort of you have the first 3 bits being how many there is. Spheres start index, and that'll just, you get in the let's call it V. You just do something like V, probably shift right 3. And then to get the number of spheres count, that'll just be like an and. Xerix. Or just 3 as well, actually. No, 7. First 3 bits. Then you want to be able to construct this thing. This will come from a start index and then a count. So it would just be start index shift left 3, ORed with the count. Bear in mind the count should probably be ANDed with 7. So the count should probably also be like take 1, and then that would just be this plus 1, because this would be 0 to 7, and the number of spheres inside of a cluster is 1 to 8. So you want to sort of offset that, right? Yeah, so I think we'll have something like this. This will just be used everywhere where we reference a cluster. Cluster sphere, spheres, range. I could call it a sphere range maybe. No, but you specifically want to use it for a cluster. Right, so it's nice and packed. Yeah, some of that will do. So here's your BVH node. Only the leaf node really needs this. Oh yeah, you need just sort of left and right. So you need a parent. when we're traversing down, we don't really need a parent anyway. So you got 6 ints, 7, 8, 9. Thankfully, if this is a leaf node, so you can check the left. If left is E32 max means this is a leaf node. And then you say if this is a leaf node, this is this guy. It's a cluster range. And that's how you can pack it down to 8 floats, or 8 units. That'd be cool. So what is this sphere thing? Yeah, so what is a sphere for a volume? Or a sphere inside of a volume. What does that mean? That's a good point. Yeah, so these are probably shared. These spheres, range of spheres, are probably shared between the BVH and the cluster tree. Could probably reuse those in some way. So this probably needs. So remember, it's in local space of the volume, right? So realistically, that is just a E32 times 3, but it's not really that. It could be packed even more, and you probably want to pack it even more because this does take up memory, and we're going to probably fix allocate these and have a maximum number of spheres for the whole game loaded up at runtime. So packing here is vital, I would say. This number can get quite big. So basically you need 10 bits for every sphere for a position. Sorry, for every axis of the position. So center position, we could call it packed. I don't know. So XYZ 30-bit. Okay, 10 bits each dimension. So I don't know what we're going to be. Got a couple extra bits there to use, but that should do. Whereas 1024 by 1024 by 1024. So we just need a radius. A radius goes up to 1024, so it's another 10 bits. So we just need 10 bits for a radius. What other information do we need? So there's the material. So we need a material in there. And all we need is a material offset, I think. That's 4 bits. See, I can actually just use bit fields. Like, if this is only on GPU, I've got bit field support. So all I really actually need is this. Like, we're just setting a GPU. Well, to be fair, this works across CPU and GPU, but yeah, we can just do this. So radius, we need 10 bits. Material index. Now this material index is actually an index into the it's an index into the instance, or So material palette index, it'll be like a index into the material palette. Index into the material palette. From the volume instance. That overrides it, right? Okay, a volume needs a default palette. Default material palette as well. So this doesn't need to be 10 bits, it just needs to be 4 bits. Because you got 0 to 16. Or 15 inclusively. Right, what else do we need on that sphere? Not much, right? So can we get this to be packed any more? So we've got 30 bits, 44 bits. So you could probably do this, you know, unfortunately 8 bytes of information. I don't think we can go any less because these are basically defining that it needs to be one 4-byte integer. Yeah. So 8 bytes is basically the minimum. So we have extra space. So we could probably just list that here. Unused. So we have right, let's just calculate this thing. 18. We have 18 bits unused. That's cool. So we can always add some more features or change, and maybe have room to change how things slightly work, which is good. What else do we need to do now? So we've done the BVH tree. We just now need to do the cluster tree. So a cluster gonna look. Could you also split these two? 32 for position, 16 for radius plus material. I'm not sure the rest of the pipeline is though. That's basically what we have, right, in a way. So we've got 30 bits, right? So that's basically one 32-bit integer there. And then this is 14 bits plus 18 unused. And this is another integer, so that's 8 bytes in total, right? I'm just trying to, like, these volume spheres reference a slot in a 1024 by 1024 by 1024 volume, so we need 10 bits on the XYZ. Oh, we could flatten the index. We could flatten the index. That's another way we can do it. So, is that right? You need less bits if you flatten it. So 1024 times 1024. Is that right? Wait a minute, wait a minute, wait a minute. Yeah, it's 1 billion. No, that's 30 bits. Where was I getting that before? Where have I done that in the past? Where it's been less? I could have sworn I did something like that in the past and it got less. Maybe not. I'm misremembering something I did in the past. Okay, so a cluster tree. So a cluster tree is just an octree. Ideally, you want all the child nodes to be. Oh no, you can't, can you? Right, so let's get this cluster tree sorted out. So this is going to be a tree of like an octree of clusters. So the root node is basically the whole model at the lowest level of detail. And you'll have references going all the way down the tree. So you'd have 8 references, and these would be the children indices. So you have 8 of those boys there. So given a cluster node, what else of information was there in this cluster? Yeah, so each one of them can have a 2x2x2 of spheres, and they can have empty slots. So that one you need to basically use this thing, this sphere range. So that could be allocated. Yeah, it's gonna have a bunch of spheres there. What is this in padded out where here? So each cluster has a bunch of spheres. Yeah, the material properties are stored on the spheres. So that's fine. 2x2x2. We could store a depth in there. I don't know how useful that would be. It might be useful. See, we know our depth. We can also know the size of a sphere. Um, hmm. Yeah, I think we might have to think about this when we build the shaders, like exactly how this one is going to work. But essentially, it's just a tree linking to more of these nodes here. with the spheres on it. So when you need to render, you somehow search this tree for the level of detail which is visible, like given the varied, given how far the camera is away from the volume and how big the volume is. The volume can be very wide or something, and it goes very close to the camera. It's very far away, for instance. You have a variable level of detail across the whole volume. So you probably will spawn a bunch of threads on the bottom part of the tree. So we might need a way to somehow quickly get access to the leaf nodes of this tree. Maybe. So if that is the case, we need to have a different way we do this data structure a bit, right? Okay. What else is missing? So we've done... Okay. So I think we can mark this off as being done. The data structure design is now done. This one and this one has still got to do this. So we've got to design the allocators. So how we're going to allocate these bundles. Or we don't have to. That one can be missed because we don't have those on GPU. How do we allocate our volumes? How do we allocate our clusters? How do we allocate our materials? This is just a pool. That's fine. But yeah, we're going to need to have custom allocators for clusters, volumes, BVH nodes. And the spheres. Well, there's one more data structure we're missing. You know, on the sphere, this would be known as the binned sphere. So this will probably be in wild space. Like, so you've gone and inspected this volume, and you've taken this. You've got the sphere now. Now you need to bin that in. Wait, do I want it in world space or view space? Probably view space. So you'll translate it all the way from local space into view space where you do the ray tracing. Then you'll probably have a reference to material at that point as well. But rather than a palette thing, this would be like a material index, like an actual material one. This needs to be a better name. The fact I've put a comment here for this is just horrible. This is a reference into... This index is used to index this array to get an actual material index to index and get one of these boys. So the fact this has to be is called material index is terrible. We probably want to call it instance material. Well, I could call it what it is, right? A material palette material index. Oh crap, I saved a new file. Remember that. Awesome. So that'd be a full-on material index. These just be binned into view space, so we probably don't care if it, like, quantizing it probably doesn't matter. But you, what other information is useful? Nothing else really. Good. Well, that's all of it. So that's. So that only needs to. It would be nice if that was 4 floats instead of 5 floats. To see if we can make this 4 U32s instead of 5. Bit of an odd number. Maybe it won't be worth it though. So there's another problem with the clusters. When the clusters get turned into, so we do a tile binning, where we bin these spheres into screen space tiles or frustum space voxels, which we have both already set up. We just got to see which ones are better. But we probably want to make some occluders, which are some occlusion volumes, which are made out of clusters. So if those are made out of clusters, we probably just want to transform a axis line bounding box into view space, and then build a basically triangulate it. Yes, you need to turn your. Yes, you don't need to worry about the cluster. Okay, so if you have your occluder, like, if your occluder, yeah, because we might do occlusion culling per cluster. So if you select a cluster, which is 2 by 2 by 2, you say, hey, I want to render this guy. You've probably got to. But you could probably write down in an array all of the clusters that you want to try and render, and then you go over all of those guys and get occlusion volumes for those. Do a software rasterizer for those, and rasterize them out to a very low resolution screen, right? And then go over the whole list again, and then see if they're occluded or not. And then those are the ones that you actually render, right? And then you bin those, they actually generate binned spheres for, right? Okay. So you have a list of, you traverse this volume cluster node, produce a array of clusters that you want, generate occluders or occlusion volume. I always call them occluders. So you call it a so what is it? So volume cluster occluder. Oh, Russ must go. I sense the wizardry from here. Oh boy. Pack spheres by skewing the grid. Oh my days. Okay, loaded. Okay, I was thinking. Science. Oh my days. So this is where they've got a radius of 1 each, right? It's interesting. It's got that glitch that we fixed in ours. Right, okay, anyway. It doesn't keep the up. Anyway, it's cool. So, right, so because you skewed the grid, they're all tightly packed even though they've got a radius of 1. Interesting. Right, because I was thinking about... That's really clever. So I was thinking about... So this is what I was thinking about in a... Was it in a 2D sort of way? Okay, so you've skewed the grid like that, where you've brought the axes in a bit. Oh, there's an axis. Yeah, I was thinking about this in a kind of a way, but not really. Wait, which one is skewed? Uh-huh. So the X is not skewed. And the other two are skewed. Yeah, I think this is kind of what I was thinking about, actually. But maybe it's not. Maybe this is... Oh no, this is skewing axes. What I was thinking about is... Ah, gotcha. This is clever. Yeah, I was thinking about offsetting the spheres themselves and doing this by offsetting the spheres. This is by doing it with a transform. Interesting. Right. I wonder. So if I were to model... Yeah, so this is the model we have, right, the dumbbell ship. It does produce it at an angle though. But... Yeah. It's interesting. Yeah, this is offsetting the spheres. Yeah, it's clever though. The way you've thought about doing it is you just skew the rather than offsetting the spheres manually, you're just doing it via the matrix. I would never have thought about that. Yeah, I was thinking about this from a 2D perspective, but I couldn't quite figure out how it would look in 3D. But this is it. You've done it. So yeah, this is the other approach we could do if we didn't want big spheres, is we could tightly pack them like this. Then you could see through so many layers. You can see through like the first... Oh, okay, maybe there is a gap technically. But yeah, there's probably you would never see this. You would probably never see that. You just assume you'll never see it. And you could probably occlude the layers behind the first layer or something like that. You could generate the model from the SDF by sampling it with a skewed grid. Right. Yeah, I see what you're saying. Yeah, I could do that, isn't it? Yeah, I'm not sure how I like the look of the model now that I see it. Because it does add a bit of restriction where everything just looks skewed in the end. Hmm. This is pretty sweet, this app. Oh. Oh, so you can always skew the grid. Oh, that's skewing the model. Yeah, yeah, yeah. True. Yeah, so the position, I think yeah. Yeah, it does change how the model will look though. Yeah. I'll think about it some more. I'll get a good old think tomorrow, see how I feel about it. But it does, my first impression is maybe not. It's kind of, it might be artistically annoying to work with when you're sort of making your stuff. Hey, very much. Are the models defined? Yeah, we're doing pretty good. We're just coming up with, like, we've got a plan. Order, whatever it is, 66. You know, let's form the Galactic Empire. Um, so yeah, we're just we've got this whole design basically. So scoped this out this morning, um, and I'm just got to finish off these guys and we can start executing it. Effectively, what we want to achieve, the whole aim, is to build a stress test scene with a bunch of models, and also test performance and test graphical features. So we kind of started doing it with it. We've got multiple model instances. Here they are. Whoa. I've got a little camera now. I'm not sure if you've seen that. And then, but we want to add like support for different LODs and clusters, so we can basically do occlusion culling and kind of goes hand in hand with an LOD system, really. Oh, and have like a variable LOD across the whole model, depending on the camera angle. But also different sizes of balls. We want to have things, balls probably down to the size of about 1.6 mil, um, up to a range of 1.6 meters. And depending on how you scale the volume, it could probably be 160 millimeters all the way up to 160 meters in a single volume. So yeah, we're just trying to basically get a whole plan together to achieve all of these things. How are they offered? They're going to be offered in there'll be an editor at some point. We'll get to that eventually. After all this has been done. But essentially it'd probably be quite I'm thinking about taking this aspect from Dreams where it's sort of like rather than storing a 10 by 10 a 1024 by 1024 by 1024 grid of spheres on disk. We'll probably just store them as a bunch of operations, like edit operations, and we'll just evaluate those at runtime instead. So this will be our sort of compression. So this will be authored in engine, saved out as this list of edits. So you basically get undo and redo history, and it would just really shrink this down to a small amount of memory versus in the many megabytes, right? Yeah, it is, isn't it? Like, it's really incredible the technology that came out of that game, and it's a shame where it ended up going. To be fair, but it's cool. It's a cool thing that it existed, and it's still available now. It's just not been developed on anymore, which is a shame. Um, but yeah, this is definitely that's definitely one aspect I want to borrow from that game is how they basically save 3D volumes of things out efficiently, and that is with a bunch of edits. Yeah, this is a 3D volume of spheres. It's not really the same thing. Though with dreams, is sun distance fields. Yeah. Are people already querying and making spiritual successors to a PC where people sell their creations? There's already this guy on Twitter who's already doing it. I'm pretty sure I saw some guy on Twitter already making a spiritual successor to Dreams. I'm not on maybe not Dreams, but maybe like having the sign distance field tool set on PC. And it wasn't the guy who makes the voxel program, it's a different person. Yeah, I think it was mainly just the tool set to actually design and edit these 3D volumes of sign distance fields. It's definitely an achievable thing. But yeah, because that's one of the most amazing things about Dreams was the tool set. Like for people to pick up and create things and not have to worry about texture mapping and making, all these different models, different levels of detail and things. Like it basically did the whole. Let's go to that video. So as soon as Unreal Engine 5 got announced with Nanite, someone who was working on Dreams made a video where they just sort of like made the Nanite demo in Dreams and just it was pretty crazy. Obviously it wasn't as detailed as theirs was, but it was basically the same thing. This is it, isn't it? Yes, Martin Nebelong. Yeah. Yeah, I don't think they'll be doing that the entire game, to be fair. Not like have a whole sort of online aspect to it. I think it's just mainly a tool, the tooling. But yeah, because Dreams was more than just the sculpting, right? Dreams had it had even like the visual programming, visual coding, and all sorts, right? So there's all that aspect to it as well. Yeah, this is just funny. So this was already a feature. Yeah, the edit thing is amazing. Like I don't know, Rosmusko, have you seen learning? Oh, okay, Alex Evans, SIGGRAPH. There's a video so you can consume it in the Gen Z way. So if you're Gen Z like me, you can consume that. Learning from failure, yeah, that's good. There's that one. There's also the slides. For it. Here it is, this boy. It's a bit big, obviously, you know, the whole deal with these PDFs that bloody ginormous. But yeah, that's got a load of good juicy info if you're looking into sort of alternative ways of rendering. But yeah, this is the Nanite demo done in Dreams. The YouTube compression destroys the quality, to be fair. But you know, obviously like the very painterly look in places, but you know, there's tons and tons of instances and just yeah. Anyway, basically replicate the whole thing. It would be cool if we could achieve something like this, but with spheres, right? With spheres that go as small as 1 mil. We'll see what we can do. It could be possible. This is why we'll have this LOD cluster system, so we can probably achieve some of that. But yeah. And he just made it all by just sculpting it like this. Just like duplicating stuff and whatever. Bananas. Yeah, made it in a couple hours, or that in a couple hours, and then some other thing as well. Such a great tool set, right? Look at that. Oh. That's just so natural. You know, you don't have to go, hang on a minute, let me create some UV map. You know. But anyway. It feels like it shouldn't work. Yeah, it is one of those, isn't it? It's just like, it just feels so ergonomic that it's just like, and it runs on a PS4. I know, right? Insane. But yeah. So anyway, we're gonna borrow that aspect with the edits to compress the data down because it's just a good deal. We're gonna yeah. So we're also gonna make it so the ball size is variables. Hopefully, going into some 1 mil. But yeah, I was just kind of just designing this so we can just execute this whole plan and see if we can make some awesome tests soon. Probably not that as awesome as that one, but you know, just something. But yeah, being very cool. So what is like occluder? So the occluder, so you've gone over all of you've traversed your cluster tree. You're gonna go here, I want that cluster, and that cluster, right? Your clusters will be, so if you say I want this cluster, and this cluster, those are going to be in local space of the, so you kind of need to know the sort of bottom left position of your cluster. You could probably do it as another packed integer, isn't it? So you'll probably have your bottom left. Okay. Left 10, bottom 10, near. And then that's 30 bits. Nice and packed. So that's 10 integers there. So you'll need that. So this combined with the world from local, you would transition that to world space, and then transition that from world space into view space. You'll be able to combine this with the view from world matrix as well, and just do that all in one multiply, or one set of multiplies and adds. So you got your occluder. Your occluder is going to be, so you go over all those cluster indices that you have in one lovely array, and you'll be able to turn that into, so you want to have some axis line bounding box in the local space of the volume turned into something in view space, which is then triangulated, right? So you're then going over all those clusters. Yeah, then you're just drawing the occluder. You don't need it as a structure. You're just drawing, wait, you'll be drawing a bunch of triangles with a depth. Some near depth, and yeah, I can't quite. Yeah, there might be some form of animation involved as well in it. This is only for static stuff we're thinking about. But yeah, I think we're going to add that in later. But yeah, I think it's possible to do the occlusion with that as well. Awesome. That's good, that's good, that's good. We don't need occluders. We might produce another array of triangles or something like that, but it should be it. Awesome. Okay, so that's the data structure stuff all done. We just got to do the design of the allocators and then design a few shaders. We might just jump straight in, to be fair. Like, I think this is sounding like, as I've gone over this and designed some data structures, I think it's becoming pretty sound. We probably just want to figure out like what shaders we need and what kind of order we want to start to do them in if we were to implement this whole new system, right? And how we can get back up and running quickly, basically. Yeah. Time for a commit. That is true. We should add this plan, models plan. So with this models plan, it's kind of my first big bit of documentation. We could probably make another folder and call it plans. I don't know, docs. Just chuck it in there. Then we'll commit that as well. Models plan.txt. Put that boy in there. Move. Git add docs. So essentially we've just like, add new model plan. Couple more things left. Before we can execute. Excellent. All right, I'll get that up onto the repo after the stream is done. Cool. Right, so that should be it for today. Next stream will be Thursday, probably start at 7:30 p.m. GMT as well. Again, same as today's stream. Where we're literally just going to work on the custom allocator design. It's probably going to be basic, probably fixed size pools or something like that. Very basic ones. We just want to know them ahead of time before we go, and then probably design what shaders that we need and how they're going to work and what order we need to make them in. And then with that, that's the plan finished, and we can just go full ham and get that done. Now, what's Kanji doing these days? Okay, let's see if someone's on Twitch. But yeah, if you guys want to, you know, I will post on Twitter someday. There's a Discord. Come check it out. If you want access to the code, if you're a Twitch subscriber or a Ko-Fi support, that's a preferred one for me. You get access to the code, and it runs on Linux and Windows. And yeah, thank you for the support for those who are already supporting me. Thank you, thank you. Let's go to Twitch and let's avoid any of the non-software and games development content. There we go, my eyes are now safe. So, who do you want to raid? Is there any C or PPs around? Good night, Jam or Toast. Thank you for coming. Good to see you. Aha, did you see what I did there? Good to see you. I see no CC. What is going on? Fair play. Man, I can't wait for the next stream. LOD and clusters part 2. That would be amazing. What is this guy programming in? I knew it, C#. I thought it was C#. Saw what the code was, and I was like, is that C#? And it was C#. Right. Let's just raid Berserker. Sorry, Berserker. There you go. Right. Yeah, have a good rest of your week. Well, I'll see you guys Thursday. Have a good Wednesday. And Thursday as well. See you Thursday. Catch you later. And what's up?